Hey everybody, I'm Mateo. Welcome to Young Engineers of Today. Hope you're ready to continue with model rockets. So we're gonna get a little bit more into the nitty-gritty of rocket design today. Discuss some of the design aspects that go into it and why you might decide to do one thing over the other. Also, I feel I should mention that there is an intense thunderstorm going on outside. I spent a little bit of time reviewing what we went over on Monday. I know it was pretty extensive. I spent a lot of time talking about it, but it's always good to have a little bit of a refresher. And I'm also gonna apologize beforehand because I am running on 2 hours of sleep. So I'm probably going to sound a little loopy, say some weird things, maybe get stuck on some tangents. Just bear with me. It's gonna happen. This is what happens when you have 2 hours of sleep. I don't recommend it, but you probably already knew that. Anyway, without further ado, let's go ahead and get started. So again, we're going to start with a little bit of review, and we'll move on to new stuff. So Monday we went over the basics, very sort of an introductory sort of thing on model rockets, why you want to use them, parts, and sort of a launch and everything like that, similarity to real rockets or big rockets or space rockets or whatever you want to call them. Model rockets are smaller versions of rockets used in spaceflight. We already knew this. Nothing crazy new there. Many of them emulate early rocket designs, however they can be whatever you want if you're patient enough. And many of them emulate early rocket designs just because most model rocket kits provide the means to create a very basic rocket, but they can be customized beyond that, like this little Saturn V rocket that's taken off from the pad over here on the right-hand side. But most of them are going to emulate very old school rockets, early rockets. So yeah, there's that. Well, why would you want to do that? Well, because they're fun, honestly. Model rockets are enjoyable to build and launch. However, they can be useful to teach the basics of aerodynamics and rocket design and construction because you can take a lot of the stuff that model rockets do and apply them on a larger scale to larger rockets, at least in a general sense. So we went over what makes up a model rocket. You've got a nose cone, you've got a body, you've got fins. No real crazy stuff there. The nose cone increases the aerodynamics. The body contains the structure and the stuff for recovery and stuff like that. The fins provide stability. They basically grab onto the air, for lack of a better term, and keep the rocket pointed upwards. The inside of the rocket, though, is a little bit more complex. You've got, of course, your engine, which makes it go up, the engine mount, which keeps the engine affixed to the body of the rocket and not flying off in some random direction. Got the recovery wadding, which protects all the stuff on the inside from the ejection charge that blows on the engine to make all the inside stuff become outside stuff. The parachute, which is part of the inside stuff, but it's meant for recovery of the rocket. Now, it doesn't necessarily have to be a parachute. It can be like a streamer, or it can be, whatever. The shock cord, which keeps the nose cone connected to the inside of the rocket. The shock cord, of course, also prevents the nose cone, the act of the nose cone blowing off from severely affecting the rocket's structural integrity or stability. So there's that. The parachute lines keep the parachute attached to the rocket. Duh. The launch lugs are there in order to keep the rocket affixed to the launch rail on the launch pad. And the launch rail essentially makes sure that the rocket is heading in an upwards direction until the rocket is going fast enough for the fins to actually engage and do their job. Then we spend some time talking about what's actually going on inside of the engine. So the actual model rocket engine is made up of a few different parts that all work together in your model rocket. You've got the clay nozzle, which is nothing more than just a shaped bit of clay that forces the thrust to actually go downwards in a very specific and small aperture, which increases the thrust and makes the rocket go upwards faster and with less propellant. The propellant is the fuel for the rocket. That's what makes it go. Once it ignites, it creates the thrust and the rocket goes. So there you go. Once the propellant runs out, then there's the delay charge and the tracking smoke. And the entire point of that is just basically to give the rocket some time to decelerate naturally before deploying the parachute. You don't want to deploy the parachute too early because A, you could damage the parachute, and B, it will slow the rocket down significantly and the rocket won't go nearly as high into the air. Also, it will be much less effective at higher speeds. It will have to counteract the acceleration of the rocket upwards, and then it will have to counteract the acceleration of the rocket downwards, and it's just, hardly ideal. Also, it creates smoke so that, you can more easily see your rocket flying through the air and stuff like that. Then the ejection charge and the clay cap can be too much. Oh, you mean the acceleration and everything? Yeah. The ejection charge burns very quickly, basically just kind of like a small explosion. In order to create enough pressure to blow the clay cap upwards. The clay cap just flies basically upwards. The clay cap is meant to protect against a lot of the heat and pressure that is created from the ejection charge. But then you've also got the recovery wadding, which provides further protection and ensures that there isn't really going to be any damage to the parachute or anything like that. But the entire point of it is to force the nose cone off and the parachute out of the rocket so that it deploys and the rocket can actually come to a much softer landing. So with all of that together, typical launch would probably look something like this. You've got it sitting on the launch pad, it ignites, it goes into a power descent, which is where the propellant is burning, and it is gaining acceleration and speed, both, because it is actually going faster. Anyway, until the propellant runs out, in which case it hits coasting flight, and it continues to coast upwards. You also might notice your rocket begin to tilt, and that's just because as the propellant burns away, the bottom part of the rocket becomes lighter, a lot of times than the top part of the rocket, depending upon how it's constructed, in which case it begins to rotate in order to compensate for that. During the coasting flight as well, the delay charge will probably also be sending off some smoke, potentially, in order to help you locate the rocket more easily. And then the ejection charge is hit. Basically explodes the clay cap off, the nose cone off, and the parachute out, so that it will actually descend and slowly, and then you can recover it. So, pretty basic stuff. No big surprises there. Rocket goes up, rocket deploys parachute, rocket comes down. I don't think you need a whole lot of review on that. But, this is all well and good, but how does it compare to full-size meant to go to space rockets? And we spent a little bit of time talking about that on Monday. There are a lot of similarities. We can go over them really quick. The payload system here on this rocket has got that orange box around it, whereas the recovery system on the model rocket on the left has got the orange box around it. And that's just because a lot of times the payload system, it can contain some form of recovery as well if the payload is meant to come back down to the Earth or something like that, more so than the rocket itself. A lot of bigger rockets aren't really meant to be reusable in the same sense that our model rocket is. And that's just because, they go up higher, so they have to, they have a lot more potential energy to counteract. Which does turn into kinetic energy as it goes down. So they have to, the parachutes have to spend more time slowing the rocket down and keeping the rocket slow. In addition, as the rocket is re-entering the atmosphere, it can hit the atmosphere and you can use the atmosphere to actually slow down a rocket very effectively. Problem being, this comes in the form of friction. It generates a lot of friction. In fact, it's enough friction a lot of the times to just make stuff burn up in the atmosphere. And so in order to sort of simplify that whole process, a lot of rockets just kind of burn up in the atmosphere, or they stay out in the in low Earth orbit or something like that, like space junk. And that's not something that we're trying to do as much anymore because that's starting to become an actual, like a cause for concern for aerospace engineers and rocket engineers and stuff like that, and people who are trying to plan missions to get satellites up there and people and things. They have to worry about that space junk because that is that stuff can do a lot of damage. So for that reason, we're trying to also reduce the amount of junk we put into space. So yeah, there's that. But if anything's going to be recovered, generally it's the payload. We're starting to become a lot better with recovering other parts of the rocket and stuff like that. So more of the rocket you'll find will be recoverable in future designs and stuff like that. But as it stands right now. Then you've got the propulsion system. So as you can see, it's just a little engine on the model rocket, and then it's the entire middle of the space rocket. And that's just because, well, a couple of reasons. One, model rockets are much lighter, so they don't have to worry about as much thrust to get it up into the air. It doesn't go as high, so you don't have to worry about as much thrust to get it up into the air. Stuff like that. On top of that, you run into an issue with space rockets where you begin to need fuel in order to lift the fuel that you have already into at least a higher altitude, if not orbit. This is something that you get diminishing returns with this. So at some point, adding more fuel to a rocket actually, will make it less efficient to the point where it can't launch. But there is still a balance to be had there, and something that aerospace engineers and stuff like that need to consider. They actually need to make sure that they're bringing enough fuel to get the rocket up into space, but not too much fuel that they're actually fighting too hard against the weight that is generated by the fuel. But they still, in a lot of cases, especially if the rocket is going up to a very high orbit, they will need some additional fuel in order to take the fuel that they have to get it into orbit up. So you need fuel for your fuel. And it's not ideal. Really the best solution a lot of times would be just to have a more efficient fuel, has a higher specific impulse and stuff like that, but that's another discussion for another day. Then you've got this pink square, and I've got it around the fin on the model rocket and around the fin on the space rocket. This is, I'm going to call it the control system, which is not exactly a 100% accurate term, but it can work. And here's why. Control systems generally refer to ailerons and flaps and rudders and stuff like that on airplanes and rockets. They are the parts of fins and things and wings that that can be controlled, hence control systems. You can make the flaps flippy flappies, and you can make the ailerons lift and lower and blah blah blah. Rudders left and right, and that's kind of what makes it a control system in that, or a control surface in that sense, because it is a surface that can be used to control the vehicle, the craft, the aircraft, the spacecraft, whatever it is. And they are very, R equals E? Not sure I follow. They are very effective, much more effective than just the straight fins that we have on our model rockets, because obviously they're controllable. They're very good for correction of large, heavy objects. They're also good for correction of large, heavy objects in the thinner atmosphere. So, there is that. And that's why fins are much simpler on model rockets, especially just because on model rockets, they're not going that high and they're light. So, and you make them out of balsa wood. So you don't need crazy control surfaces on a model rocket. But those are some similarities, stabilizers there. And yeah, so just as a side note here, this isn't really related to much of anything, but you may have noticed in the past, certainly, that there are many rockets that don't actually have fins. Why is that? I mean, it seems kind of weird because, I've been harping on like the model rocket's fins are very important, and you've probably seen a whole bunch of rockets that have fins, but then there are rockets that don't have fins, and that seems kind of odd. It seems kind of odd to deny yourself a means of control and stability. But here's the thing. They still have the same amount of control and stability, and in many situations, more. Um, than a finned rocket would. And you might be like, well, what? I'll tell you why that is. They have something called Gimbal Thrust. So it's basically just you've got a guidance computer in it and a bunch of servos on the nozzle and a gyroscope. And the gyroscope detects the precession or tilt or wobble of the rocket as it's lifting off. It might be like, okay, so it's actually tilting, 10 degrees, and it shouldn't be. So we need to fix this. So the guidance computer will pick up on that. Well, the gyroscope will pick up on the fact that that's off kilter. The guidance computer will take that information from the gyroscope and go like, okay, so we need to do something to fix this. And what it will do is it will actually engage the servos in the thruster or the nozzle and tilt it so that the thruster or nozzle is providing force that is counter to the precession or tilting of the rocket. So rather than using fins to grip the air and sort of keep the rocket pointing in an upwards direction, the nozzle at the bottom itself will actually tilt back and forth in order to keep the rocket pointed in an upwards direction, which is pretty cool. And like I said, more effective in many situations because in order for a fin to work, you kind of need air, right? You need to have some sort of atmosphere or gas or something like that for the fin to grab onto. A gimbal thruster, that's not so. You can just tilt the nozzle and the rocket will correct itself. So it's very good for very high atmosphere situations. It's good even in a sense for space. But yeah, so um, well, gimbal thrust is cool, but you're never really going to see it on a model rocket just because it's so complex, relatively speaking. Especially for something like a model rocket, which is a foot to 2 feet tall, and nice, a foot to 2 feet tall, and made of cardboard and balsa wood. So there's that. But anyway, the main difference between space rockets and model rockets is their cost and power. Oh, that wasn't mine. That was a friend, and it was a stuffed Garfield. Um, but yeah, the space rockets and model rockets, their cost and power and size and stuff like that. But they work the same way. They have some form of stabilization mechanism. They have the ability to go up. They have thrust that provides them the ability to go up. They're very aerodynamically minded. They're generally propelled by some sort of chemical reaction. It's all very similar in that sense. But that actually does it for the first presentation. So now we move on to the second one. Just taking a moment to wake myself up. because the lack of sleep is really starting to hit me now. All right, here we go. So the second presentation is going to be a lot more on a lot more into the design decisions that go into creating a model rocket. Why you'd want to do A over B or X over Y or whatever. We're going to talk about fins, we're going to talk about motors, and we're going to talk about recovery systems. We're probably really only going to get through fins today. It's probably going to be about as far as we get. And then, you know, we'll leave motors and even potentially recovery systems for Monday. So yeah, fins, as we've already established, are the main stabilizer on a rocket. Stabilizers being what stabilize the rocket's trajectory as it flies through the air. In other words, stabilizers make sure that the rocket doesn't just fly every which way upon launch, just for the most part upwards. But however, how your fins are structured can affect how your rocket flies. So let's take a look at that. Before continuing, I want to basically talk to you guys about the forces at work on the fin. In this case, drag. Drag is simply the force of the surrounding air on the fin working to slow down the rocket. Think of it like friction, but from the air itself. So, you know, if you've ever been riding in a car and the window's down and you stick your hand out so your palm is facing towards the ground and you can feel sort of like the air push your hand back, and you can kind of do like the woo, I'm flying thing, and like, you know, kind of like lift up your hand and like tilt your hand upwards and have it like force your hand up further into the air and then tilt it back downwards and have it force your hand back down towards the ground and stuff like that. That's like drag. That's not like drag, that is drag. To feel the effect more strongly, you can point your palm forward so it's facing towards the front of the car, and then suddenly you'll feel the air a whole lot as the car is moving, and you feel like you're being, you know, your arm is being pulled backwards. That's drag in action. That is something that aerospace engineers have to worry about all the time. In fact, anybody who makes any sort of vehicle has to worry about drag, because as long as there is an atmosphere, as long as there is movement in that atmosphere, drag happens. Sometimes you don't really have to worry about it as much. Most of the time, if you're trying to make a fuel-efficient vehicle of some sort, you'll have to factor in drag. And that's certainly no exception. In fact, that is especially true with rocketry. So drag on a fin comes in two forms. You've got induced drag and profile drag. As an interesting side note, as you can see, the air is affecting this rocket in this diagram here, this lovely diagram from the Kerbal Space Program Forum. The airflow is creating this drag. That is to say, the rocket moving upwards, is creating an airflow, which is by extension creating drag. Now, here's the thing. This is just kind of another, I guess, benefit that liquid engines have over solid engines. At some point, you'll probably be able to gather my opinion on liquid engines versus solid engines. So I'll just go ahead and say it right now. They both have their purpose, they both have their place, but I am generally of the opinion that liquid engines are superior for a number of different reasons. One of them being this particular situation. A solid fuel engine, once you turn it on, you cannot control how much it burns or how fast it burns. You cannot turn it off until it runs out of fuel. You can, in indirect ways, control how much it burns and how fast it burns by how you pack the fuel inside. But on the whole, you have no control over that. It's going to burn as fast as it's going to burn. It's going to burn as long as it's going to burn. And it's just going to continue burning until it can't burn no more. So for that reason, solid rockets can be less, well, let me not say for that reason yet, but solid rockets can be less efficient, and in fact are less efficient than liquid rockets. Now here's the deal, solid rockets, solid fuel generates a whole metric butt ton of thrust. It is really great for getting something heavy off the ground and getting that acceleration started. However, a lot of that fuel is wasted. And it's because of this a lot of times that liquid fuel engines, when they're first lifting off the ground, they tend to run at a reduced percentage of maximum thrust. Like they'll be running at, like, maybe 70 to 80% max thrust, at least in the beginning. Now, why might you think that is? The case. Why might you think that is the case, I should say? Why would you not want your rocket to be running at 100% thrust right off the ground? Sure, there are a couple of reasons, but there's one in particular I'm thinking of that's related to what we're going over right now. Appreciate it, Cohen. Save fuel. Okay. But why? Wouldn't you want the rocket to be accelerating as fast as you can in order to have as much upward momentum as possible? Okay, so why not? Because I will say, at some point, that rocket will be ratcheted up to 100% thrust. Otherwise, why would you have, 100% thrust on a rocket? Why not just bring down the maximum thrust on a rocket to 80% to make it more fuel efficient? But at some point, well, there's that too. It could cause harm to people on the ground. But I'm thinking of something specifically related to what we've been going over. There is a point in the launch after the rocket has gained some altitude that it will go up to 100% thrust. It's just not right on the ground. Yeah, exactly, Matteo. Literally, the air is thicker the closer you are to the ground. The air creates more drag the closer you are to the ground. So you want to wait until you've gotten to thinner air before you start ratcheting up the thrust. Otherwise, you're just wasting fuel. You're just sitting there going like, all right, here we go, maximum power. And there's sort of a maximum acceleration that a rocket can hit before drag really starts to hit it hard. And so in order to overcome drag, well, you can, increase the aerodynamic profile of the rocket, but you can also just get to an area where there's less air. And once you get to that area where there's less air, then you can go like, all right, maximum full power, and then thrust it up to 100%. Thrust it up to 100%. It's not really, doesn't really make any sense. Not what I'm trying to say. You turn it up to 100% thrust. And then you really start, like redlining that rocket. So for that reason, that's sort of another tick in favor of liquid rockets or liquid fuel rockets, because you can control when that fuel, like how much thrust the rocket is putting out compared to its maximum. A solid rocket booster, solid fuel rocket, you're going to turn it on, it's going to go, 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 go. 100% forever, all the time until it runs out of fuel. And that's just going to be inefficient in the lower atmosphere because there's just too much air. But again, solid fuel does provide a very, very generous specific impulse. So that's why, like the space shuttle had two solid rocket boosters on either side of it because it provided a whole lot of power to get that thing off the ground because it was super duper heavy, like ridiculously heavy. So yeah. So anyway, induced drag and profile drag. Induced drag is created when the rocket fins use the air to correct a rocket's path. Basically when they're, for lack of a better term, gripping the air in order to fix the rocket so it's heading upwards. Most model rockets do very well at flying straight up, so in general, induced drag tends to be pretty low for them. But you know, you could have like a little bit of precession or a little bit of wobbling or whatever, in which case you'll have more induced drag as the fins sort of grip the air and kind of wrench the rocket back into an upwards flying direction. But yeah, on the whole, induced drag, not always crazy high. There is going to be some of it, but induced drag is almost kind of more the useful drag in measured amounts. You know, you don't want too much induced drag because too much drag is bad. But if induced drag is your control, you want at least a little bit of induced drag. Too little induced drag, there's nothing stopping your rocket from just like going sideways, literally, and, you know, flying in a completely unintended and undesired direction. Now, profile drag is the nastier of the two, because profile drag just comes from the shape of the fin itself and is always present under velocity in an atmosphere no matter what. And to go back to our sort of analogy with cars, you can think of a boxy car driving down the highway versus a sleek one. A boxy one is going to have more profile drag. It's drag that's created from the profile of the fin, hence profile drag. It's something that's always going to be there, and it doesn't really benefit the rocket a whole lot. So you kind of want to minimize profile drag because, you know, it's just going to slow your rocket down. Ooh, that was some nice thunder. Anyway, for this reason, you'll want to spend some time considering different fin designs in order to reduce the ever-present profile drag. But there's another concept I want to go over with you guys. In order to spend some time talking about actual fin design, it's good to understand a concept called a Reynolds number. So a Reynolds number is just simply a number that helps describe how turbulent a fluid like air is. And you might be going, okay, that almost made sense. Air isn't a fluid, it's a gas. And you would be half right. When we speak in a popular sense, like, you know, like you go to the doctor and you have the flu or whatever, and they're all like, you know, just take plenty of fluids and, you know, call me in the morning and let me know how you feel and keep yourself hydrated and blah, 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 blah. In a popular sense, fluids are, you know, water and stuff. However, in a physics sense, fluids and liquids aren't exactly the same thing. You might want to think about the word fluid itself, what it can be used to describe. Think of like martial arts, and there's always that one monk that's just like going around everybody else's like punches and kicks and stuff like that, just kind of like effortlessly sidestepping them and like parrying their attacks and stuff. Yeah, in a physical sense, you could be like, I'm always taking fluids. I'm just breathing air all the time. That's why I'm not dead. But you know, like you get where the doctor's trying to go with that. So generally, you try to provide a more helpful answer. But anyway, you know, you think about that martial artist like sidestepping all those things and parrying all those different attacks and stuff like that. And it's a very fluid style. Like it's very much moving around everything and adjusting to the situation, and you know, well, he's very fluid. He flows. He's not solid. He's not standing there in place with his feet planted to the ground necessarily. So in a physics sense, both liquids and gases are considered fluids. So a liquid is a fluid, but a fluid isn't necessarily a liquid. A fluid could be a gas. If you take like a fluid dynamics course at college, if you decide to continue with aerospace or, mechanical engineering or something like that, it's kind of you'll spend some time going over the dynamics of airflow because that is part of a fluid dynamics class. So yeah, that can be a little strange to think about because in a physics sense, a fluid is also a gas. So anyway, a Reynolds number describes whether a fluid is very smooth in its movement, also known as laminate, or if it's very bumpy and chaotic, or turbulent. So, if plane flying through the air, pilot's like, oh, we're going to hit some turbulence. And then the plane starts, bumping and jiggling and stuff like that. That's because it's hitting turbulent air. That is air that has no uniform direction to it. It's moving in many different directions, and there's eddies and pockets and competing currents and stuff like that. Laminate is an ideal sort of fluids condition. It's very easy to predict. It's very easy to work with. It's when all of everything is just moving in one direction nicely. In fact, that's why this picture is here a second time. This picture is actually I'm not sure what filter this is, but it's basically showing it's a specially edited picture to show the movement of air above a candle. This is actually a picture of a candle and the air moving above it. So that sort of dark rod at the bottom, that's the candle itself. You can actually maybe see the wick coming off of the top of it right here. Kind of looks like a weirdo stick of dynamite. And then the flame is somewhere in here, and this is all the hot air rising off the flame. All of this hot air right here is very laminate air. It's all moving in one uniform direction, right? Then right about here, boom, suddenly the air is just going nutso. This is turbulent air, very turbulent, chaotic air. So there you go, a very visual representation of laminate and turbulent. But you can use Reynolds numbers to predict how your fins will perform. We'll take a moment, though, to look at how a Reynolds number is calculated. First, is it necessary? Nah, it isn't. I don't want to, start giving you guys all kinds of like crazy, additional information necessarily, but it's kind of cool to see how we can use mathematics to predict something like air movement. So this right here is the equation that gives you a Reynolds number. Notice how it's got two equal signs. That's just because there are two forms of the equation that you can use in order to get a Reynolds number. But a Reynolds number can not only be used to predict the turbulence of a fluid, but also where that turbulence begins on something, which is pretty neat, I think. But anyway, you've got the result, which is the RE, the Reynolds number. You've got the density of the fluid, which is the rho right there, that weird looking P thing. That's actually a Greek letter, rho. You've got the V, which is the velocity of the fluid. We're just going to look at this leftmost one, which is in the middle. So that's how the rho is the density of the fluid. So you think of density like in a literal sense, like water versus air. Water is going to be a denser fluid than air is, right? The velocity of the fluid is how fast that fluid is moving. So, winds and stuff like that. Then you've got the L, which is the length of the object that the fluid is passing over. So like a wing or a fin, for instance. And then you've got the dynamic viscosity, which is that mu on the bottom, which is that weird looking U. Dynamic viscosity. So viscosity has to do with kind of like a thickness. So think of molasses and water. A moment. That's true. It does look like an upside down H. So molasses is a very viscous fluid. whereas water is certainly much less viscous. So now, dynamic viscosity, sort of how the viscosity changes, how resistant it is to changes in viscosity, things like that. So, all of those things together will give you a number which relates to the turbulence or lack thereof of a fluid. Strangely enough, it'll make more sense, as you get further along with this kind of stuff if you decide to dyn means power divided by force. Yeah, yeah, I can. But yeah, so anyway, we've mentioned how the Reynolds number relates back to how fins perform, but how does that work exactly? Well, we can use a Reynolds number to see if the fins are long enough to be useful. So you see in the little diagram that I've got here on the right-hand side, you've got those red lines signifying the movement of air. Obviously, the squigglier the red line, the more chaotic or turbulent the movement of air. The straighter the red line, the more laminate or smoother the flow of air. So in that sense, we can figure out where right, but so that's the root, but it also means in a sense change as well. That the meaning has changed. It's not always it's not always going to be like a one-to-one sort of comparison with roots and stuff like that, because the the usage of them can change the meaning of them over time. Although that is a good point. But like things like decimate, think about how decimate means in a lot of popular senses to utterly destroy. Technically speaking, the history of decimate is to destroy a tenth of something. It came from when Roman legions would be, there was a decimation of Roman legions, in which case 1 out of every 10 soldiers was killed. Like decimal, that sort of thing. But nowadays we say decimate, and it is kind of synonymous with just like utterly and completely destroyed, like it was decimated. But that's not the original root of the word. Sometimes these things can change. Although that may not have been where you were going with that. You may have just been sharing an interesting factoid, in which case, thank you. I think that is pretty interesting. But yeah, so here's the thing. Smaller fins won't be as effective because fins need to basically find purchase on laminate air in order to be able to correct a rocket's path. Fins don't do as well, especially depending upon the design of the fins, don't do as well in turbulent air. They'll have a harder time keeping the rocket straight and stable, because the air is moving in all kinds of different directions, and they're using the direction of that air, in order to keep the rocket heading in the same direction. So laminate air is much more effective for fins. So we want to have fins that are large enough to extend past the turbulent part of the air created by the rocket body, because as you can see, we've got a nose cone on this thing, which is increasing the aerodynamics of the rocket, but it's also shoving air off to the side, which is creating turbulence in and of itself. So the air right beside the rocket body, because it's the air that's pushed aside by the nose cone, is going to be pretty turbulent. Air further away from the rocket body is not going to be as affected by the nose cone and the air around it pushing it, so it's going to be generally more laminate. So we want fins that are large enough to reach that laminate air in order to essentially find purchase there and keep a rocket moving upwards smoothly. So larger and longer fins will be able to make use of the laminate air to keep the rocket steady. But that's not all that goes into fin design. Having larger fins means that we have to worry about profile drag more, because they're going to have more of it. So we run into a bit of a conundrum. We have to have fins that are large enough in order to reach the laminate air, but not so large that profile drag just totally overcomes everything. But we can affect that too. So now the actual shape of a fin comes into play. Now we worry about the actual shape of the fin as opposed to the size of it. We've established that the size needs to be large enough in order for it to work with laminated air. But the shape as well has become important because we have to worry about profile drag and stuff like that. And it becomes far more important how we construct the fin. So we know a large fin is probably ideal to a certain extent, not too large. But what about the shape of the fin? So why don't you guys take a guess? Take a look at this stuff. Take a look at these fin designs. We got 4 here. So you're going to say far left. So number 1. So 1, 2, 3, or 4. You're guessing 1. What about other people? Got another vote for 1. All right, so 2 votes for 1. Might be surprised by this. Maybe 2? Okay, maybe 2. So here's the deal. You might have thought it was 1 or 3, because a lot of those are featured in airplane designs, So you've got the elliptical fin, you've got the swept fin and stuff like that. You might think that those are sort of the most effective designs for that reason, because they're used in aerospace already and they're a very well-established design. But you also have to take into account that the ratio of the wingspan versus the size of the aircraft is very different from rockets. In the case of airplanes, this ratio is very high, meaning the wings are very large relative to the rest of the vehicle. They have to be, because the wings are the main way of providing lift on an airplane. Very different from rockets. Rockets, it's the thrust, the chemical energy providing the thrust. With airplanes, it's the fluid dynamics sort of forcing the wings to provide lift. So in the case of rockets, you want the span of the fins to be as small as possible. This goes directly counter to as large as possible, but it's a balancing act. You want to strike a balance between low drag and sufficient control. So rockets have to also be much more efficient with their usage of fuel, and they tend to fight against the air rather than use it to their advantage like planes do. Planes use the air in order to provide themselves lift. Rockets are basically just trying to get through the air as fast as possible so they don't have to deal with it anymore. So the fins serve a different purpose than the wings do on planes. Obviously, the wings on planes also provide stability. A lot of times that's reserved for the back of the plane in order to provide additional stability and control. But regardless, fins serve a purely stabilization purpose on rockets. They're really not meant to provide additional lift for a rocket. All of the lift is going to be performed by the actual chemical reaction happening on the rocket. So for that reason, elliptical fins, swept fins, things like that, on top of the fact that they tend to do poorly in situations with low Reynolds numbers in general, they tend to not really be the best answer. See, again, because you can have large wings on planes, the wings can be large enough in order to overcome the turbulent air by the plane body, because there's plenty of wing on either side of the plane. The wingspan is large enough that it's taking advantage of a lot of laminate air. Now the fin near the body of the rocket is also thicker and longer, so we take these fins, these wings, whatever. They also tend to be thicker the closer they get to the base of the fin, closer they get to the body of whatever they're providing lift for. And that also tends to increase drag and exacerbate its issue with low Reynolds numbers, because it creates more turbulence. The rocket is moving more slowly. It's all bad. You can make the fin thinner towards the end, like in the second picture, which reduces the amount of drag, but that tends to be very difficult to make, especially if you're just sort of like whittling fins yourself out of balsa wood or something like that, and it's hard to guarantee strength and consistency. On top of that, you've got, as you can see, if we're looking at the side view, as it's sort of creating that elliptical shape, it's smaller near the end, which is going to be the part that finds the laminate air. So you're going to have the less effective and efficient part of the fin be the part that's actually in the most effective and efficient part of the air. So funnily enough, rectangular and parallelogram style fins do very, very well at lower Reynolds numbers. In addition, even though they have a little bit of increased drag, they perform well enough to offset that and then some. On top of that, the fact that for instance, this first one, the rectangular one, the fact that the surface area is the same on the side throughout the entire thing means that you are not becoming less efficient as you get closer to the edge of the fin, by virtue of the fact that you've got less surface area. It's actually just as efficient. So, you know, if you manage to make the body of the rocket more aerodynamic and have to worry less about turbulence near the body of the rocket, well, that's just an additional bonus as opposed to compensating or recovering some of your lost control with an elliptical fin. So now that's not to say that your rockets won't fly well necessarily with elliptical fins, but it just tends to fly better with rectangular ones. And yeah, maybe that all seemed a bit counterintuitive, but math and physics are funny like that sometimes. And that's exactly why engineering is an iterative process. Sometimes these crazy seeming ideas, like having a rectangular fin, just straight up a rectangle on the side of the thing. Obviously, it's got a swept cross section like wings do, but regardless, it's just a big old rectangle. Sometimes those are the ones that end up working out the best. And with that, we've actually finished fins. So I'm going to go ahead and call it for a day. We're going to do the poll questions and then leave it open for question and answer time. And then you guys are more than welcome to head out and have a wonderful weekend. And we'll meet up again on Monday and continue with our good old discussion about model rockets and design.